Okay, so that was a wonderful introduction. I won't go through it all again. Boxes, heaps, and stacks. What we're talking about today. Who am I, first of all? The easiest way to find me is on the internet as Tim Clicks. And this is the book that I've written, which you may or may not recognize. Okay, so this seems like a talk about Rust, but actually, it's really a talk about computers, because this talk will only make sense if we explain not just the syntax of box and referencing and dereferencing, but also actually what those mean and what a computer is doing when it applies those operations. At the end of the talk, I would like you to know more about what a stack is, what a heap is, as well as other things like pointer, reference, memory address, what the ownership system is and what the lifetime system is, and one or two other things even. In this room and on the live stream, there will be people that actually know a lot more than me about these topics. So please do participate. Feel free to interrupt me during the talk or ask questions on the live stream. You're very welcome, and I'll do my best to answer. Or at least put it down as something that I need to learn about. So just to be very clear about which type of box we are referring to, it's this syntax you would have seen in Rust with a capital B box, and we have less than and greater than, and then some type T in the middle. Normally when we create a variable, we'll have the variable name and maybe sort of an optional data type, and then we create something. We have sort of the value on the right side. But when we put things in a box, we've got this different syntax where we start with the box and it's a new. And then this kind of magically works. And what's going on there is the essence of this talk. Because creating a box is different because it allows us to link two different parts of memory which enable dynamic memory allocation, or enables data structures to be created that can grow and shrink like string does and like vector does. But first I want to just provide you with some permission for like not knowing what is happening. So I want to explain my own learning path by just explaining how, when I was thinking of this metaphor, I was wondering like, what do we mean by box? I assumed, because before I learned Rust, I spent about a decade or a little bit more in Python. And I assumed that box must mean something that could like open or shut, or perhaps it was, maybe there was like a byte at the start and a byte at the end, you know, some sort of tag left and right, and then the value was in the middle. None of that is true. Absolutely none of it is true. So I had the completely wrong mental model, which is quite useful when you try and learn a language where it's kind of essential. But like the first place to look perhaps would be the standard libraries documentation. The point of there's one sentence, which is a box is a pointer type for heap allocation. That's no good unless you already know what pointer type means. You need to know what a heap is, and also you need to know what a memory allocation is. Without that prior knowledge, the sentence is meaningless. So, and it turns out that actually I think that there's one other really important part of this discussion, which is the ownership system as well. Because the box takes ownership of the value that you're giving it. It's one of its essential. So if I added my own addition to that sentence, I would include explicitly that we're talking about the ownership system as well. So we've got this problem that before we can answer what a box is, we've got some further questions like, what is a pointer? Because we need to know what a pointer type is. We need to know what a heap is. we need to know what a memory allocation is. What's an own value? Okay. Let's define pointer as a memory address that a compiler has for which the compiler has information about the type that the pointer is referring to, or the pointer is pointing to. So I am an integer, and I have a pointer over here that is pointing to the integer. The compiler knows the width in memory that the integer takes up in RAM. But I've actually introduced some new jargon. So now we have a new question that we need to answer. What is a memory address? A memory address is a number in that the CPU or the computer hardware can actually use to translate to some place on a physical chip. The mechanics of how this happens is a few degrees beyond the scope of this talk. But essentially, your operating system and your CPU work together to convert that number into a physical place in RAM. So I'm just going to say it's sort of what that means. So we can think of a memory address in x86, 64, in the particular CPU architecture that you're unless you're doing microcontrollers, which we just saw earlier, is between 0 and 2 to the 64 to the -1. At least we've got a little bit more information to be able to define what a pointer is. A pointer is the memory. There's some length, it's known at compile time, and the first definition was a pointer type for heap allocation. We've got 2 out of 5 questions answered. So we need to now answer, like, what is a pointer? All of these types are actually embedded the same way. So this first one here is a reference to T, or what we call a shared reference to T. And this ampersand mute keyword is does anyone know what the term for this is? Yeah, so there are 2 terms. Unique reference would be the C++ terminology, and in Rust we tend to use the term mutable reference. They actually mean sort of the same thing. And then these 2 are a little bit different. Const T, and I'll just get rid of that. It didn't quite work. Const T and mute T, or with the stars. These are raw pointers. And lastly, so the raw pointer is less useful to most Rust programmers. I have fn. It turns out that functions are actually pointers as well. But instead of pointing to data, they point to some space in memory that has been marked as executable. The CPU encodes program code as integers and in memory addresses as well. It just happens to execute them. Now, I'll get out of this. But we actually are really interested in this bottom one, which is box. It has the same internal representation as all of the others. They actually look to, in the final binary, as exactly the same thing. This is what we call a zero-cost abstraction. The added semantics that we get with box, which involve its ownership of the value inside it, are a compile-timed construct. Many of these types are called references. I've been using that terminology without defining it. So now we have another question, like, what is a reference? A reference is actually a pointer that also has lifetime information. So what do I mean by a lifetime? If I imagine a program started at 0, and then at the end of the program, or when it exits, it's at 10. A value might be valid from point like time 2 to time 5. And if I attempt to access that variable at time 6, 7, or 8, those would be invalid accesses. Or if I had started to access it before it had been initialized, say at T1, that would be invalid. The compiler actually does a similar thing with lifetimes. Rust's difficult syntax, the reason why Rust requires you to sometimes use lifetime annotations is because it uses this information to guarantee that you will not access memory at the wrong time. You can't access some value before it has been initialized. That is, you cannot access a variable before it's been defined, like if the name doesn't exist. And you will get an error at compile time. By the way, and as a Python or an ex-Python programmer, this was very, very handy. I don't have to worry about name error anymore. We're like creating a bit of a stack of questions, which is slightly intentional. So we've got this definition of a lifetime of t is some span of time for which accessing a reference to t returns t. And by t there, I mean a value of some data type. Now, if you are a systems programmer, or if you've used C++ or C or some other systems language, and you know what a stack frame is, one thing to note is that Rust's lifetime system actually is bound to the stack frame of the function. But I think it's an interesting thing to explore, and I invite you to do so, but I'm not going to talk more about that because I don't want to scare people who don't know what a stack frame is. We have most of the questions answered, although we keep adding more questions. So I don't know, hopefully we'll get to the end. We now need to answer this one, which is like, what is the heap? I'm going to answer that by introducing another piece of jargon, which is the stack. So that's a problem. The stack is so we've talked about an address space. So the address space is this region of memory between 0 and 2 to the power of 64. And the top of that address space, like right up towards the maximum value, is where the stack lives. And right down the bottom towards 0, although not including 0, actually, is where the heap starts. That is only relevant in the sense of if they collide for some reason, that's actually a big problem. And in fact, there are protections in place to make sure that your stack doesn't grow too large. This is where the term stack overflow comes from. Anyway, I should start defining these terms. The stack is a region of memory of the address space that is reserved for function calls. It works really, really quickly because its memory model is very fast. Everything that exists in the stack is of fixed size. Additionally, there is actually some hardware support for the stack. There is a CPU register called the stack pointer, and variables that live inside the stack tend to be very small. So what ends up happening is a lot of the CPU cache, or if you call into a function, you'll typically keep all of your variables either in registers or in a CPU cache that's very close to the computer. And if you are a language like Rust and you really care about performance, that's where you want your data to live. Because the alternative is that you have references and pointers, and that means that you have some memory address in some other part of the address space that you need to jump from the top of the address space down to the bottom, and then find the part in memory where you're referring to, and then you'll come back and forward and hop around. And that kind of hopping, or alternatively, you can go even further. We have references to references to references. This is a very slow process that involves like a lot of accounting. there's a lot of extra work that is involved for accessing memory from the heap. There's actually so much extra work that it's configurable. If you want to really look into this, the Rust provides the ability for you to control how the access works. This is called an allocator. And one other thing to note, just because it was relevant to the previous discussion, is that microcontrollers typically don't give you access to dynamic memory, or you don't get a heap. You only have a stack. Everything needs to be of fixed size. So you can think of a pointer, or like you can think of the box type as kind of a link between the stack and the heap. It provides you with the ability to access this very flexible address space, but provide a very but keep a fixed size reference inside the stack. So our functions are always in the stack, but when we need flexibility, because we want a data type that can shrink or grow, or for some other reason, because we might want to share references between functions to some memory, it needs to live in the heap, then we need some kind of way to refer back to it. And the box is that type because of its ownership semantics. I'll just talk quickly about what a memory allocation is. That's a request for memory from the operating system. And the ownership system was the last one too. Was there a question?
Well, the last expression, it has a little asterisk to it, right? So you don't necessarily go to the operating system.
Okay, yeah.
It depends.
It depends, right? So I put sort of in a couple of the other ones, but I didn't hear. Now, the point was just for the just so that we get it in the microphone, that we don't always get it from the operating system, or at least you might have asked for, say, 10 kilobytes previously, and then you decided to tell the operating system that I don't need 2 kilobytes of that, and then subsequently you asked for some more memory, but you already had it available. And this is what I mean by, so you could think of a very simplistic way to implement this would be to always ask for more memory from the OS. Alternatively, you could be smarter and try to group requests for memory of very small data types into to a single larger request, because presumably asking for memory from the OS is going to take some time, and so we don't want to do that very frequently. So this is configurable, but it's a complex, difficult subject, and maybe I'll just put a hidden asterisk in there.
It's true for the default.
Yeah, it is true for the default case. Right, yeah, okay, yeah, that's right. It's always tricky when you try to write a talk for hopefully a general audience without scaring too many people. Hopefully there aren't too many people who are just more confused at this point. There is one final concept that we should define, and this is ownership. And this is like the easiest thing to define in the whole of Rust, right? No one has any issues with borrowing or owners. Okay, so like what is an owner? In Rust, so the reason, I think this is another metaphor that is difficult because it does not match our intuition for what the plain English definition is. If you look in a dictionary for property and owner, it will probably say something like has exclusive access, or the ability to, if I think of property rights, if I own my house and like its little piece of land because I have like a little single family house, I can tell people who don't belong there to leave, and they would be required to leave by law. And but that has no association with property or ownership in Rust. The owner does not have the ability to say, no, you cannot access my data type. In fact, even when you, even if you are the owner and like your scope is the owner, and you have a method call, you'll notice that all method calls have the ampersand mute self. So you still actually need to borrow from yourself. And this is because the only thing that the owner does is safely delete everything that it owns. So you could think of, and that is the owner, when it is dropped, it calls drop on the things that it owns. The end. That's all. The owner has no special power. They can't go to court and force your data to come back. You cannot go. So now we get to go touch a little bit of code. I wanted to show the difference of, I've got A here is our kind of normal 1, 2, 3, and B is in a box. And hopefully I can, and I'm just going to click playground link. And if I create a main function, and then I call math, this should fail to compile, hopefully, as long as I know a little bit about Rust. So what this is saying, first of all, is that it doesn't know how to add a value of, let's say this is, we guarantee, let's say we say it's an I32, and this one here. So the values, in these are the same. So it should, in principle, work okay. It's saying I know how to add lots of other things, but I don't know how to add these two types. I can't add I32 to a box of I32. In fact, we need to add a star, and this is not a multiplication. What this is a request is of Rust to go follow and get out what is inside the box and bring its context back into local scope. It's called dereferencing. So now we get a different compiler error, which talks about the, I need to print. So we should, this is all fine. So using box can be a little bit clunky, or it can feel less comfortable because you kind of get these kind of syntactic problems. But I wanted to show you, and we can put in anything that we want. Oh, actually, I will get to the next slide because it's important. Like, why would we do this? The standard thing that we want to do is like, why would we use a box, is to return a reference to some local variable. So we could assume that we've got some difficult or complex structure. Oh, this is, sorry, I had a typo. I meant to change this. I can create A, which is some difficult or large thing. and then I can place it in the heap. So A is at first a local variable. And then after I call box, this difficult or large object is sent to the heap. And then a pointer is returned from the function. So just an integer comes back, but actually this difficult thing actually moves to the heap. And the good thing about the heap when you're dealing with functions and references is that the lifetime of difficult or of A is no longer bound to the function call itself. So normally if this was not here, if I was just returning large, the caller, the function that called build, would be the owner of large, and then when that function ended or when the variable came out of scope, it would be deleted. And yeah, box provides us a little bit of flexibility. We can also use box to create a vector of trait objects. Now, the difficult thing about a trait object is that it does not have a size that's determined at compile time. So what this is saying is, like, I want a vector. We can think of that as a list of box din display. Does anyone know what is happening here? Hands up, we've got 2 hands at the back.
We want a vector with structured implement display.
So right, so we're saying we would like, this is a vector of objects that implement display. So if we had this, and this pattern is actually implemented I found it in GitHub, so this is quite hard to read, sorry. You can see here that this person has created, it's in line 25, sorry. They have a trait of fuzz target, so this is and the specific types that exist within this vector are all different sizes. But because they implement fuzz target impl, they can all live in the same vector. Rust does normally not allow things of different types to be in one vector, because it likes to know of exactly how wide everything is in RAM, because its preference is to put things on the stack, because the stack is faster. In this case, if I go, I might play around with this. Sorry, I keep irritating the people with the mic. So I've got some vector, and I need to create a mutable vector, and this answers a bad name. Let's say it's like printable things. Ja, super. Okay, so what we're trying to do is create a function that, or some object that standard, I think it's standard format display. So Rust will allow me to use the absolute path in the names, saying it doesn't need to be mutable, saying you never use it, buddy. There's no need for it to be mutable, but it's a valid code. It will actually compile and do nothing. So thanks, Rust. So we can push our friendly 1, 2, 3 vec, and also printable. I should have given it a short name. Push a character. And I would like to just add an emoji in there, but I don't have one. So ampersand, an @ sign will have to do. And it's now saying that you need to actually put these in the box, because you can't actually put the objects in there directly. So you're cheating.
This error message is so nice.
One of the things I really like about Rust is, like, it can be a better programmer than me. Like, I don't need. I honestly feel that I learn. Like, one of the things I like about the Rust compiler is, like, it feels like a coach to me.
Reference is a book.
Yeah. It's really nice. Well, the box is such a common. It's such an important part of Rust that it's useful to be able to, or it's important to be able to give really helpful messages. Now I'm going to change things just a little bit because I want to show what happens if you, let's say we've got our difficult type again. This time it's not large. In fact, it's 0 size. And I'm putting this in the box. First it's saying, so it's saying that difficult does not implement debug. And what that means is the compiler doesn't know what I want when I tried, so I can't just, the compiler doesn't know how to convert difficult to a string. And so it won't allow you to put anything into any vector. Instead, you need to be able to you need to actually do what you've said, which is like only rely on the trait that you have defined. The other thing that's important is this trait object will only implement one of them, even though debug, I think, relies on display. Or does display? No, I'm going to stop there.
It's independent.
Yeah, they're independent. I should stop kind of going off track. One other thing that you may wish to do is that they've got A, B, and C here. And let's say we want, and this might be, say, small, medium, large. And then I want to provide some sort of other category. Now, if I have multiple selection variables, how much memory, this is 1 kilobyte. So this is an array of 1024 bytes. Now, you should only need 1 byte to encode all of these 3, because they, in fact, just any bit pattern that's different will be sufficient. But you need 1 kilobyte here. So if I had multiple variables, like S1 was selection small, and let S2 is selection medium. Counterintuitively, this will actually take 2 kilobytes of space, because Rust will always make them every enum the same size, and the size must be able to fit the widest or longest variant in the, must be able to fit the widest variant. And so if I put box, suddenly the size goes down to the size of 1 box, which is 8 bytes. There's a question at the back.
Isn't this only the case if it's mutable? Because as long as I can't edit it and I directly assign a small, it should be small.
That's something I'm going to check, and that's a very good question. Let's say that I have 2 immutable variables, like these 2 here, and I only ever create those 2. In fact, I essentially never use large or other. If I comment them out, my code will still run. So effectively, they're irrelevant. The question is, in that case, is the compiler not smart enough to just erase this large variant and just use the smallest or the type of what you've actually used? Because these are all immutable variables. Isn't that enough? My understanding, and I want to double check this, can you please correct me in the comments if I'm wrong, because I'm going to say something that is likely to make someone like perk up. Okay, first of all, when I'm talking more about Rust here, so this is a little bit off topic, but immutable in Rust is a lie. When we use this term, we say mutable and immutable. Now this is false. Rust, because immutable variables are still mutable. That's why we have this notion of interior mutability. What? Okay, so allow me to explain if I may. So immutable works conceptually most of the time, but what is actually guaranteed by Rust is that two unique references or two mutable references will never exist. So there will never be two writers of the same data. If, however, you are if you own the, I'm getting myself into trouble. If you have that the mutable reference yourself, or maybe its owner, if you can guarantee, and this is what cell does, the cell type provides interior mutability. You can swap what is being referred to, and so it can pretend to be immutable, even though things are changing underneath. Now, that still doesn't completely answer your question, because you said to me, but Tim, you will never use that variant in your entire code base. I still think that, I know that you'll get a compiler warning saying these variants are never used, but I don't think that Rust will erase all of the access to those unused variants. Like, I don't think that it will create a type that is different than what you've written in source code. Now, I think
the only way the Rust compiler is allowed to delete the symbol if it's unable to inline every case and there is no unsafe functions and no references away from it. Because everything else, either you can swap it or C can do weird stuff, and only then you can save the whole space, but then the symbol will completely disappear.
Yeah,
But anything else, it will allocate the full kilobyte and the byte. And if you have 4 of these on the stack, your program will just randomly crash in the default runtime under Windows, Linux, and Mac.
Yeah. Okay, so I just want to get some of that on microphone, so hopefully I can replay this correct. So the Rust compiler will only erase code, or will, if it can, under certain guarantees, and those guarantees include the fact that there is no unsafe, there are no other references into the data, but essentially, even if you never use large or never use other, Rust will still is required to assume that somehow other might appear in your program, and therefore will include the whole kilobyte. Alternatively, this is a much more niche area, but if you write a compiler or you have lots of intern strings, you can save a wonderful amount of like 1 byte. Oh, sorry, no, 8 bytes actually. 1 word width of by using a box2 str, stir with a little case s, rather than using a string. And like you say, well, what is a box to a string? Or a little case s string. This is a span of bytes that is guaranteed to be UTF-8. There's a massive downside to going with the box, and that is you cannot mutate the box. Like, you cannot mutate the string. Or you can't grow it. You can modify the data that you've got internally, but you can't actually go and change it. Okay, box, by the way, is also the basis for collection types such as vector and string. String, by the way, is a vector as well. Actually, there's a massive asterisk there. It's actually not box if you go and look at the internals. Yeah?
You just got a warning that your battery's on.
Yeah, that'll be a good time to finish. No. it turns out that because of the way that, because of some really nitty-gritty internals, the implementation is a little bit more complicated, but conceptually it works. And but the biggest thing you will see Rust Box being used for is recursive data structures. And if I wanted to implement a linked list in Rust, I would call for box, because otherwise, if I didn't, oh, that's the end, I would try to create a type that's of infinite size. And with that, I think we'll skip the looking through the other sections of the books, and I shall say thank you and done.